Today we're going to be talking about section 5.7 and 6.7 from your notes, which are dealing with polygons, in particular regular polygons, and finding sums of angles and that sort of thing. So before I get into the notes, I want to quickly show you this angle measures in convex polygons worksheet. This is the one that you worked on the other day. So we're looking here for some patterns. So I've already filled in my table here for the number of sides and number of triangles in every one of our shapes. So we can see here that every shape is going to have 2 less triangles than it does for the number of sides. So 4 becomes 2, 5 becomes 3, 6 becomes 4. I'm always 2 less when I start to count those triangles. The sum of the angles then is always multiplied by that number of triangles, because we took and used that process of splitting my figure into a group of triangles. Those triangles all add up to be 180. We know that already. So here I know now that my formula here, if I go down to the bottom, is going to be based on that n minus 2. So my number of triangles is always that number of sides minus 2, and then my sum of the angles will then be that n minus 2 times 180. And you can see our example here of using 21 as my number of sides. That's important because that's going to show up again today. So if I go back to our notes here, this is section 5.7. We'll start with the triangle sum theorem. So the triangle sum theorem says that the sum of all of the angles in a triangle is 180 degrees. Okay, we found that already. We proved that before back when we were doing triangles, but that is a fact that we're going to use again today. Okay, quadrilaterals are kind of the same thing. We just have to think every quadrilateral, if I connect across one of my diagonals, will then make sure that I have just 2 triangles. So if I connect my diagonals, I get 2 triangles, and I would say then that the sum of all of the angles in a quadrilateral is the 2 times 180, which is 360 degrees. So a triangle, that's for a quadrilateral. Now we're going to take that and go in general for a polygon. So for a polygon, it does depend on the number of sides, so that needs to be incorporated somehow. So we're going to say that the sum of all of the angles in a convex polygon is going to be n minus 2 times 180, and that's degrees, okay? Where that n is really the number of sides. So I'm taking the number of sides, subtracting 2 away from it, and I'm multiplying by 180. For the first practice problem here then, I have in ABC, which is a triangle, the angles are in a ratio of 1 to 2 to 3. So this ratio means then that if one angle had a measurement of 1, the next one would be twice that, and the last one would be 3 times that. Now we know that doesn't actually work because that doesn't add up to be 180. So these things must be kind of like multipliers on each of those angles. So I need to figure out what is the basic angle and then kind of build up from there. So what I'm going to do is I'm going to call my first one x, which makes my middle one 2x, and makes my last one 3x. Essentially what I'm doing there is I'm tacking an x onto every one of those numbers. When I do that and then I add them together, that is summing all of my angles together, adding them all up. If I'm adding them all up, I know that in a triangle those have to equal 180. So if I do 1x plus 2x plus 3x, that gives me 6x. It's equal to 180. I can then divide by 6 on both sides, and x is going to equal 30. Well, I'm asked here to find angles A, B, and C. So angle A, if I'm starting with that as my smallest angle, that's what I'm going to consider to be my first one. That's going to be the 30. So I'm going to say the measure of angle A is equal to 30 degrees. The measure of angle B is going to be my next biggest one. If I look at my sides here, I can tell that side's a little bit smaller than my last side. So that's going to be my next one, which is going to be times 2. So that's 2x, or 2 times 30, which gives me 60. And then finally I have my measurement of angle C. It's going to be 3 times that 30, which is going to be my 90 degrees. So I'm taking and finding x, putting those x's with all of my numbers, solving for that x, and then plugging it back in, finding each individual angle. Be careful on questions like this. Sometimes I don't ask you specifically for all of the angles. Sometimes I ask you just for some of them. So be careful of what I'm actually asking for there. Next one here is going to be number 2. Number 2 is asking us to find the sum of the interior angles of a pentagon and a hexagon. So I have a pentagon here. We could try and draw in all of our triangles, or we now have our theorem that can help us. So our theorem up here for polygon sum says that I'm going to do n minus 2 times 180. So I'm going to take my 5, I'm going to subtract 2, and I'm going to multiply it by 180. Well, 5 minus 2 is 3 times 180. 3 times 180 gives me 540, which is in fact the interior angles all added together in a polygon, or in a pentagon. Then we'll do a hexagon. Well, a hexagon has 6 sides, so this is going to be 6 minus 2 times 180. Put that 6 minus 2 in parentheses. 6 minus 2 gives me 4. 4 times 180 gives me 720. And there's my next answer. So really just using that equation that we have to kind of work through each one of these. Number 3, and the measure of the angles of a quadrilateral are in the ratio of 2, 3, 4 to 6. What are the measures of the angles? So again, just like with the triangle, this would be if I had an angle measure of 2, the next one would be 3, then 4, then 6. We know again that that doesn't work because a quadrilateral needs to add up to be 360. So I'm going to put some x's in there. So I'm going to have 2x plus 3x plus 4x plus 6x is equal to 360. If I go ahead and add those all together, 2 and 3 is 5, plus 4 and 6 is another 10, so 15. So 15x is equal to 360. If I divide by 15 and divide by 15, x is going to equal 24. So 24 is kind of my base angle that I'm working with, but I don't actually have any that are just that. My smallest one is actually 2 times that. So I'm going to do 2 times 24, which gives me 48. That's one angle. Then I would also do 3 times 24, which is another angle. That's going to be 72. Do 4 times 24, which is 96. And finally 6 times 24, which is 144. Those 4 are all my angle measures. Finally, down here on the bottom, we have to give the sum of the measures of interior angles in a convex octagon. So we're talking about an octagon that has 8 sides. So I'm going to use my formula that I was talking about, the n minus 2 times 180, where n is going to be my number of sides, which is 8. So this is going to be 8 minus 2 times 180. Well, 8 minus 2 gives me 6. 6 times 180 gives me 1,080. This is my answer. Okay, so that's going to finish up 5-7, but we're going to also the other side of this page and talk about 6-7. So 6-7 now takes us from polygons and talking about their measures and their sum to now talking about regular polygons. When we talk about polygons, we've defined that word regular previously, but we want to make sure that we're all on the same page there. So we're going to say a regular polygon is a convex polygon. Okay, again, meaning that we can stay entirely inside the shape. So a convex polygon whose angles and sides are all congruent. So all of my angles and all of my sides are congruent. Okay, I have some examples here. When we have a regular triangle, we call that an equilateral triangle because I have all of my equal sides. These are all equal, and all of my angles would have been equal as well. Okay, same thing, square is kind of that special regular quadrilateral. All of my sides are equal and all of my angles are equal. In fact, they're all right angles. Then we have our pentagons and our hexagons. Here I have an octagon, I could have a heptagon, a nonagon, a decagon, a dodecagon. All those words that we talked about previously, I can have all those things. We also know that if I go beyond 10, we just call it that number gon. Okay, and we're going to start to call that an n-gon. Okay. As I start to break down what regular actually means, regular means that it's both equilateral and what we call equiangular. So we'll start with equilateral. Equilateral just means that all sides of a polygon are congruent. Okay, we just got finished talking about a quadrilateral, so a rhombus is an equilateral quadrilateral where all of those sides are the same length, not necessarily the angles, but for sure all of the sides. And equiangular is kind of the opposite of that. All of the angles are the same. Okay, so all of those angles of a polygon are congruent. Okay, that's going to be our rectangle when we start to talk about our quadrilateral. So all of the angles are the same. If I combine the two, then I get regular, which is our square when we're talking about quadrilateral. So next thing, let's go ahead and talk about some symmetry. So when we're talking about polygons and being regular, there's lots of symmetry involved because I have lots of equal pieces. I have equal angles, I have equal sides, all of those things start to play into each other. So I have two types of symmetry that we need to talk about now. We talked about reflectional symmetry and dimensional symmetry. So first thing I'm going to talk about are those lines of symmetry, which is really getting at that reflectional symmetry. So I'm going to say that there are n symmetry lines. Okay, what that means, that n is the same number of sides. So if I'm in an n-gon, okay, that could be 8 sides, that could be 12 sides, whatever the number is that shows up in front of the gon, or if I give it one of its special names, it possesses n symmetry lines. Okay, those lines can vary a little bit. So we're going to say that the locations vary. But I do know a couple things about those lines. Those lines are always going to bisect a side or an angle, or there are some that actually do both. They bisect a side and an angle. Sorry, on the other side, or both. Okay, so I bisect either a side or an angle, or I bisect both. Okay, number 2 then is our rotational symmetry. Number 2 says that there are n-fold rotational symmetries. Okay, that means that if I take my shape and I spin it 360 degrees, it's going to completely match up with itself n times. Really, whenever I get another side to match where the other side used to be, I'm going to get the same shape again. Okay, and so that's that n-fold rotational symmetry. So example 1 here, I just want to show you, or the first example here, I want to show you where those lines of symmetry sit in this shape, which this one here is a polygon. So I'm going to grab a ruler just so we can look at these a little more exact. But really what I'm doing here is my first line of symmetry is going to go straight down the middle there. Now when I look at that line of symmetry, I'm going through my angle up here at the top. I'm going to bisect that angle, so I get 2 equal pieces. I am also the perpendicular bisector to my side down here on the bottom. Okay, now that's going to follow for every one of my sides. So, sorry, I'm trying not to rotate my paper here too much. And I can draw in all of these lines of symmetry. Every single one in this pentagon is going to have an angle bisector and a perpendicular bisector to the side. Okay? I'm gonna make a quick note. In this pentagon, I have each is a perpendicular bisector and an angle bisector. Okay, and that actually works whenever this is odd. So if I have an odd number of sides, my lines of symmetry are going to be both a perpendicular bisector and an angle bisector. That changes slightly once I get to an even number of sides, which is what I'm going to talk about here with my hexagon. So with my hexagon here, I have 6 sides. I can draw in my first line of symmetry right down the middle, but there I see that this actually bisects 2 angles. So I bisect the angle at the top and the angle at the bottom, and I have now 4 equal angles based on those. Okay, I can also bisect another pair of angles here with this line, and I can do the same thing going over here to this side. Alright, now here's the problem. I have 3 lines of symmetry there, but the theorem I just said I should have n lines of symmetry, and here I have 6 sides, so I should have 6 lines of symmetry. So this is not the only type of line that I have. If I look here, I also would have my horizontal line here. If I draw on that horizontal line, that doesn't go through any angles, but it does bisect my sides. So my last type of line of symmetry is going to go through both sides that it intersects, and it's going to bisect those all at those nice perpendicular right angles. Okay, so when it's even, I'm going to have half as angle bisectors and half as perpendicular bisectors. Okay, those are just good notes to kind of keep track of and know what our lines of symmetry are going to look like. Alright, let's do some quick practice on these and then you can get started with your homework for today. So for practice, number 1, I want to find the number of n-fold rotations in a regular heptagon A, B, C, D, E, F, G. So heptagon, if we remember, is 7 sides, or if I wasn't sure, I could count how many letters I have here, or I do have a picture here that I could draw in all of my or count all of my sides. So I have 7 sides. So if I am talking rotational symmetry, well, my n-fold rotations is the number of rotations that I have. So I'm going to have 7-fold rotational symmetry. So I would have 7 rotations in that regular heptagon. I can also draw in all of my lines of symmetry. First one is always usually the easiest to draw in is my nice vertical line. I don't have a horizontal line here because every one of my lines is going to go through a vertex and the side opposite it. So I'm going to draw in all of these here. And I know that based on my theorem, I should have 7 of these when I am done. Let's see if I can get them all on here quickly. Couple more here. Got E, but I got one more going this way. And G. Alright, so now I have my point there in the center where they all meet. Okay. By the way, here, this point here in the center is what we call the center of symmetry. Okay, or the symmetry center of that figure. It's where all the symmetry lines meet. And I did have 7 lines here that I just drew in. And I can count them all if I want. I got 1, 2, 3, 4, 5, 6, and 7. Okay, so I do have all 7 lines there in my picture. Last one, let's talk about number 2 here. I want to find the measure of an interior angle of a regular octagon and a regular decagon. Now, this is slightly different than the ones we just did. This is an interior angle, not the sum of the interior angles. However, I'm going to use the sum. So in an octagon, I know that I have 8 angles, or 8 sides. If I knew the sum of every octagon, I know all my angles need to be the same, and I could split them between all 8. So that's going to be my first step, is I want to find the sum. So to find the sum, I use my formula, which is 8 minus 2 times 180. Well, 8 minus 2 is 6 times 180 gives me 1080 for my sum of all of my angles. Now I don't want 1080. I want to take and divide that by the number of angles. Well, for a 9, I have 8 sides, so I have 8 angles as well. 80 divided by 8 gives me 135 for that angle. And I can do the same thing for a decagon. A decagon has 10 sides, so I'm going to start by finding my sum. 10 minus 2 times 180. Minus 2 is 8 times the 180. 8 times 180 gives me 1440. Finally, I can divide by my number of angles, which is 10. Gives me a final answer for one angle of 144. Okay, that finishes up our notes for today. So we're going to go ahead and stop there, and we'll pick up with our next section tomorrow.